Lecture 29 of Physics 72 introduces inductance, both mutual inductance and self-inductance. This can be seen in subchapters 30.1 and 30.2 of University Physics. Please take time to read the objectives. While there are calculations involved in this lecture, a solid conceptual understanding of what inductance is and how it plays a role in circuits is crucial to making the next lectures clear. From the previous lesson, we've seen how changing magnetic fields can induce currents to conductors. This lecture tries to provide the foundation for how electromagnetic induction is applied. A lot of these applications can be seen in everyday life, such as induction cookers, wireless charging, and transformers. We will see how coiling conductors, so coiling conductors, as you can see on the left, this is what you call an inductor, and we'll get to that more later. It's a toroidal one. Okay, so we'll see how coiling conductors open the possibilities to bending electricity and magnetism for our benefit. The first part of this lecture introduces the concept of inductance, from how two conducting coils interact with each other, especially when there are time-varying currents applied. Recall that from a previous lesson on magnetism in parallel wires, two wires with currents running through them produce attractive or repulsive forces depending on how the relative current directions are oriented. Now, for simplicity's sake, we assume that these currents are constant, so that means they're not going to change over time. We begin the lesson with a modification of the setup from the previous slide. We look at two coils instead of parallel wires. We also look at time-varying currents, which we will denote by the small letter I instead of constant currents written as big letter I. Here we have the two coils. Only one of them is specified more. So the geometry of coil 1, as we can see here, has N1 turns, has a cross-sectional area A, and has a length of L. Then we also have a second coil with N2 turns, but then we don't necessarily have to specify its A and its L, which we will get into later. Okay, now we look at the lengthwise cross-section of that diagram. We're going to chop it in half lengthwise for ease of explanation. We want to see how two coils interact with each other when time-changing currents are driven to it. And as with anything dealing with electromagnetic induction, we will take our sweet time explaining this step by step, as it can get very dizzy very fast. Okay, our story begins by introducing a current small I1 to coil 1, the bigger coil with N1 turns. So it doesn't really matter if coil 1 or coil 2 is the bigger coil. Eventually it all smoothens out in the end. Ampere's law tells us that a solenoidal magnetic field B is produced and should be proportional to I1, as we know that the magnetic field for a solenoid is B equals mu naught N I1. It is then worth noting that a fraction of this B is responsible for the magnetic flux through coil 2, which we then call phi sub B2. Thus, we can say that magnetic flux through coil 2 is proportional to the solenoidal magnetic field from coil 1. By transitivity, we can then say that the total magnetic flux through coil 2 should be proportional to I1. Since coil 2 has N2 turns, let's express the total magnetic flux as N2 phi B2. So far, no current is induced in coil 2 for now, since the current in I1 isn't really changing. So given that constant currents are not our thing anymore, let's spice things up by varying I1 as time goes by. B should change since it's dependent on I1, and this then varies phi sub B2. Faraday's law then tells us that some EMF must be induced on coil 2. A slight change can be seen in the added N2 factor because the EMF is proportional to the total magnetic flux. So it's not just negative d phi over dt. Since since coil 2 has N2 turns, the total EMF induced should also be proportional to the total number of coils that coil 2 has. So from step 1, we know that the total flux through coil 2 is proportional to the current running through coil 1. To have a working equation, we should assign a proportionality constant. So let's call this proportionality constant M21 for now. It's kind of specific, but we'll get to that later. This is a bit of a jump, but M21 is our mutual inductance, and its expression can be obtained by isolating it from the previous equation we have in step 3. We'll get to the far right side of the equation in step 6, this one. because it can get confusing that we swap the indices, but this encircled one is a case when we put the current in I2 and try to observe how it induces a current in coil 1. But we'll get to that later. So going back to the equation in step 3, we take the time derivative. We obtain an expression that relates changes in magnetic flux in coil 2 to varying currents in coil 1. Applying Faraday's law, we can relate induced current in coil 2 because of a negative change in the current in coil 1. And after that, we should be done with this case. So to reiterate, step 5 tells you that the induced EMFs in coil 2 are due to time-changing currents in coil 1. The thing is, if we reverse the process, as I said in step 4, so instead of having the time-varying current in I1, we place it in I2. So our coil 2 is the one that carries the time-changing current. It turns out that it produces an induced EMF in coil 1. So there's this mirror effect. The opposite case should work. What's more surprising is that this proportionality constant that we get from this opposite case is always equal to the one that we got from the first case. Therefore, you have mutual inductance. The next two slides offer a detailed recap of what we just discussed. You may pause the video to have a better look. The summary continues on this slide. It's worth emphasizing again that varying currents in one coil produce induced EMFs on a nearby coil. So it doesn't really matter whether your current or your time-changing current is in coil 1 or in coil 2. Let's go over some comments with mutual inductance. Magnetism is a topic rich with nuances and surprises, and things can go very interesting very fast in cases when magnetic materials are involved. So in this table, magnetic materials are the ones with some value of mu that's not necessarily equal to the permeability of free space. Because of this, we remind ourselves that what we've solved so far only works in vacuum. We'll soon see that mutual inductance in vacuum only depends on the geometry of coils. Notice that this geometry-only dependence in vacuum property is shared with capacitance, as we've seen in a few lessons before. So it's a welcome parallelism between magnetism and electricity. You can say that inductance is the magnetic counterpart of capacitance in electricity. When magnetic materials are involved, we assign a relative permeability constant K sub m to characterize this material. Notice that we do the same with dielectrics in electricity. Except in electricity, it's kappa. When this Km is not constant, magnetic flux of one coil loses its direct proportionality to the current of the other coil, and mutual inductance now depends on the material properties as well as the currents, so not just geometry. Because of that, for the purposes of Physics 72, we'll just focus on cases in vacuum. At least we can breathe easier for now. Going back to the important equations dealing with mutual inductance, two coils are related by their mutually induced EMFs and are given by these equations. So for when you're introducing the time-changing current in coil 1, E2 is equal to negative M21 dI1 over dt. And if you work with the opposite case, if you're introducing the time-changing current in coil 2, E1 is equal to negative M12 dI2 over dt. So as stated a while ago, opposite cases still have the same value for mutual inductance. So instead of writing a lot of indices, let's just call it M. Now the SI unit, well, first, let's go with them being equal. So it really doesn't matter if you're looking at N2 or you're looking at N1. They should have the same value. What's important is this whole numerator should have the same numerical index, and then the denominator should have the index of the other coil. Then the inductance SI unit should be Henry, and 1 Henry is 1 Weber over ampere. Now we try to obtain a more specific expression for M. Going back to the original figure, we specify the cross-section of coil 1 to be A. Then we're asked to define the mutual inductance M and find out if it is indeed purely dependent on geometry in vacuum. So we first express the field of a solenoid to one that we know already, and the exception that we change small n1 to big N1 over L for now. We then re-express mutual inductance in terms of the product of B1 and A. So we're going to change phi B2 to B1 times A, and with the assumption that your magnetic field is just parallel to the area vector. So if we flesh out and direct substitute B1 to M, we have this equation. And notice that all we need to do now is cancel out the i's here. So we could cancel out I here and I here. And eventually, we have an expression for M that is independent of currents and is just dependent on the geometry of the system. Particularly, the geometry-dependent terms here would be N1 and N2, the number of coils in the solenoid, A being the cross-sectional area of coil 1, and L being the length of coil 1. This slide just specifies the variables used for M. You may pause for reference. Let's try using our expression that we got in a quick example. You may pause the video for a longer glance of the question. Notice that all of the values given are just dependent on geometry. So it's assumed that the system is in vacuum for our convenience. Now, using our equation for M, mu naught N1 N2 A over L, direct substitution gives us the following expression. And we have to keep in mind that the area of a circle, or our cross-sectional area, is pi r squared. So all we need to do is basically divide the diameter by 2, and then you get your radius. All we need to do is to confirm that we'll get the same answer, or this answer in our calculations. It's 6.32 times 10 raised to the negative 6 henries. The answer is there. I'll leave the question in the slide as an exercise. It uses the other set of equations where M is used. It's particularly the one relating induced EMFs in one coil due to changing currents in the other coil. So these equations on the right here. Okay. The next few slides cover some concept questions. So here is the first one. An ideal solenoid carries a current I. Another solenoid is wrapped around the first solenoid, resulting in mutual inductance M. So it's the same setup from a while ago. If the current in the first solenoid is doubled, what is the total magnetic flux on the second solenoid? So keep in mind that to solve this problem, we will be using the general expression for mutual inductance. So what we need to do is multiply the currents on both sides of the equation, so we can place it here. And after that, doubling the current in the first solenoid basically doubles the total magnetic flux, which is Mi, of the second solenoid. The answer should be D. Trying another question, an ideal solenoid carries a current I. Another solenoid is wrapped around the first solenoid. Well, you get the point. It's the same setup. If the current in the first solenoid is doubled, what is the resulting mutual inductance? So instead of looking for total magnetic flux in the previous question, we're looking for how it changes mutual inductance. So to give a hint to this question, remember one of the more important details about M in vacuum. The answer should be C. M should just be geometry dependent in vacuum, and changing currents should not change its value. Now, before we move on to another form of inductance, let's put a face to the mutual inductance in seeing its practical uses. Fairly common application is in household transformers or step-down transformers. Most households in the country operate using alternating currents and are ramped up to a maximum of 220 volts. If you've ever tried plugging in an appliance bought abroad, your guardians may warn you not to plug it in directly as the gadgets are tuned to operating in 110 volts, particularly the ones in the States. These devices overload if you do, and you're going to have a bad time. These transformers will transform the voltages coming in from the socket to the device so you can make them work without any troubles. These are done using coils, the same ones we've been understanding previously. Alternating currents mean that some current I being delivered to the transformer is constantly changing, inducing some EMF to another coil in the transformer to be delivered to the device. The voltage delivered by this EMF to the device is tuned using the geometry of the coils. So an application closer to recent times is wireless charging. Newer phones and devices, AirPods for example, use the concept of cable-less charging for neatness and convenience. Also, it looks very cool. Placing your devices close to the charging pod allows the coils of the pod and the device to interact, even if they are not connected physically by wires. So you can see the pod lighting up in response to the presence of the phone. Most inductive chargers aren't really this fancy though. Let's move on to the next topic, or self-inductance. We explore more in detail what inductance is, beyond it being a proportionality constant. We also try to see what coils contribute to circuits. So far, all the circuits that we discussed in Physics 72 had constant EMF sources, particularly the ones we discussed in Kirchhoff's law. Considering that we already deal with coils and electromagnetic induction, we begin to explore how sources of varying EMF can affect the system. Now, should we replace this constant source with a time-varying source, we take note that the current I will also change, and changing currents introduces changes in B as well as the magnetic flux through its closed loop. This causes a self-induced electromotive force in the circuit itself. Anytime currents change in closed loops, electromagnetic induction is sure to follow. But more often than not, tiny changes in current in single-loop circuits produce almost imperceptible induction effects. One way to magnify this effect is when we coil up parts of the wire or introduce circuit elements which are coils themselves to the system. Looking at this element, the total magnetic flux should be proportional to the current as with previous configurations. Instead of the total magnetic flux being dependent on the current of another coil, it is proportional to its own current. We introduce a new proportionality constant which we will call self-inductance and is given by L. So the equation is N times phi sub B, total magnetic flux on the left-hand side, is equal to L times I, because total magnetic flux should be proportional to current. Notice that it looks almost identical to our expression for mutual inductance, but then we don't have the numbered indices. Going back to the proportionality equation, varying the current I will also vary the total magnetic flux through a single loop of coil. But the thing is, if you vary the total magnetic flux, you're only changing phi, not N. That's because we're taking N to be constant. No changing of geometry. With Faraday's law for induced EMFs, we have an equation for it. It's basically E equals negative L di over dt. The negative sign arises from the fact that any induced EMF acts to oppose the change, which is basically Lenz's law in action. Again, notice its similarity to EMFs induced by pairs of coils and mutual inductance. The coils we've been talking about so far have a special name for practical uses. They're called inductors. These inductors basically oppose changes in currents, which occur a lot in circuits fed by AC. They offer more control in the circuits as well. As we're dealing with them, it is important for us to know how voltage drops when passing through an inductor. Considering that EMF is in units of voltage, the potential drop across opposite nodes of the inductor, A and B, is given by this equation. So VA minus VB is equal to VAB, and we're using that order because our assumed direction for current runs by A first. And that's equal to L di over dt. Now, I forgot to mention that inductance L is how inductors are classified when you buy them in electronics stores. Notice that in the absence of varying currents, or when di over dt is equal to 0, no voltage drop occurs in the inductor or through it, as it acts as a simple conducting wire. How the negative sign isn't present in the expression, because remember that EMF is equal to the negative of L di over dt, or how inductors come to be compatible with Kirchhoff's law, even though the electric field that deals with electromagnetic induction is non-conservative. We see this discussed in detail in 30.2 of University Physics. We try to omit this discussion for now for our scope. We try to understand more about this inductor with this concept example. So a current I flowing from A to B passes through an inductor of inductance L. It is observed that the potential at B is higher than the potential at A. The question is, which of the following describes the current passing through the inductor? Increasing, decreasing, or constant? Again, two things to note, that VB is greater than VA, and we must determine the rate of change of the inductor. Clearly, it's not constant, else VB should be equal to VA. To answer the problem, we use the voltage equation for our inductor. If VB is greater than VA, then that means the left-hand side should be negative. From your vast knowledge of equations, this means that the right-hand side should also be negative. As L cannot have a negative value, notice that it's the same case for capacitance C or resistance R. This only means that di over dt should be negative as well. From this, we know that the current should be decreasing. Let's take a step back on the calculations and describe inductors qualitatively by answering two questions. First, what is the physical significance of inductance L? Now, Say that your induced EMF is constant. So from the equation EMF equals negative L di over dt, you have two factors on the right side. You have L and di over dt. A larger L would mean a smaller rate of current change. So if you have large values of inductors, it offers greater resistance to the changes of current. Now, it turns out that this relationship works even if EMF isn't constant. Secondly, what's the use of an inductor in a circuit? As inductance is a measure of resistance to changes in current, inductors basically help control these changes in case they present danger to our circuit elements, or if we want to control how these current variations affect our circuits. And industrial scale applications for these inductors can be seen in power plants. In ill weather, lightning strikes that hit towers in power plants cause voltage spikes, which can spell doom for the conductors affected. So to counter that, large inductors then act as a line of defense for these sudden current changes so that they won't be as damaged. Now, similar to what we did for mutual inductance, this example asks us to show how we can obtain a more specific expression for L. We already know that L is equal to N times phi sub B over I, but then let's expand on it more. As what we did with mutual inductance, we first start by determining the magnetic fields produced by these coils. Coils offer solenoidal magnetic fields, so we first express B specifically in terms of what we know. We can also expand small n equal to big N over I, or over L, sorry. We use our definition of L so far, and use direct substitution. Combining the two expressions above, we get the result that the problem is looking for. Now, our expression for L should be equal to mu naught times A times N squared over L. Its only difference with the expression obtained from mutual inductance is that we have N squared instead of N sub 1 times N sub 2. Otherwise, L and M are dimensionally equivalent, which should be the case. I'll leave this example as an exercise. It deals with polynomial derivatives, which should be easy for those already taking Physics 72. So this last example uses actual values, so it's worth exploring. So in this example, we have an inductor that has an inductance of 0.26 henries and carries a current in the direction shown. So it's moving from B to A, moving to the left. And it's also decreasing at a uniform rate. So di over dt is equal to negative 0.018 amperes per second. We're supposed to look for the induced EMF, the self-induced EMF. And the second question is asking for whether which node, A or B, is at a higher potential. So the first answer is obtained by direct substitution. You know that EMF is equal to negative LdI over dt, and the values are already supplied by the problem. The induced EMF should be equal to 4.68 millivolts, which is rather small compared to the usual voltage supplied. The second question may be answered by VAB is equal to positive LdI over dt. Now, since di over dt is less than 0, the left-hand side should be negative. This means that A should be at a lower potential. So this is it for inductance. Thank you for listening.